It was on sale.
Gauss's law is what I was in the middle of talking about. What it says, once again, without all the details of how I led up to it, is that the amount of, if you imagine some closed surface, closed meaning that there's no way to get from the inside to the outside without passing through the surface. So a sphere would be a closed surface. A hemisphere would not be a closed surface. A hemisphere and a circle on the bottom of it would make up a closed surface. But anyhow, if you have a closed surface, the amount of electric flux passing through that surface is proportional to the amount of charge inside that surface. The proportionality constant is a number called the permittivity of a vacuum. It's related to the Coulomb's law constant. So what a big chunk of section 3 is about is seeing how various special cases follow from this very general principle. And I'll run through a few examples of that, and you'll do a few more examples of that for homework. So let's say, for example, that you have a uniformly charged sphere, maybe a pith ball like I was demonstrating the first day. And we want to show that, well, basically what I'm going to do is prove something that I simply asserted a few weeks ago, which is that the field of a charged sphere is the same as if you had that amount of charge located at a single point at its center. I tried to take how to use Gauss's law and divide it up into sort of a step-by-step recipe that you could refer to when you're doing the homework. The first step is you have to know what the field looks like. Draw yourself a picture is probably a good idea. So step 1, there's our uniformly charged sphere. When it's one of these general problems where you're just calling the charge Q, you normally think of it as being positive. If you then apply the result to a charge that's actually negative, the fact that you're putting in a negative number for Q will turn everything around and it'll all be fine. So, little charged ball, and as I've probably mentioned a few times before, the electric field at any point around it will point radially outward like that. Step 2, Gauss's law refers to a surface. Total flux through a surface is proportional to the charge inside that surface. Well, if you're going to use Gauss's law, you have to have a surface in mind. So pick the surface that you'll use in Gauss's law. This surface should contain the point where you want to find the electric field. So if you're solving a problem that says, find the electric field a distance r from the center of this charge, you want a surface that's a distance r from the center of that charge. You also want to take advantage of the symmetries of the situation, like here, where it's a spherical charge distribution. Turns out a sphere makes the math an awful lot easier than if you picked some other shape, like a cube or something like that. Would be much harder to use. So step 2, there's our charge Q. We imagine a surface of radius r around it. And as we already decided back in step 1, at any point on the surface, the field points radially outward like that. Step 3, Gauss's law refers to the flux passing through that surface. So figure out some sort of an expression for the flux. Find the flux is the way I phrased it there. Well, in general, the flux is the integral of E dot dA, but one of the things you want to do, choosing your surface back in step 2, is if at all possible, you want to pick a surface that the field is constant on, because then instead of integrating, you can just say E times A. So that's what I've done here. Every point on the surface is the same distance from the charge, plus the angle between E and the area vector is the same everywhere on this surface. The area vector for any little piece of this sphere, that points right straight out also. So E and dA have the same angle between them everywhere also. So since E theta since E and theta are constant, integral of E dot dA is just equal to E times A, which is what's pretty much always going to happen if you can find a good Gaussian surface. The surface area of a sphere is 4 pi r squared. If you don't happen to remember that, there's a place on one of the later pages of your reference handout where you can look that up. There's a section that has all sorts of background mathematical information. There's a little table of integrals. There's some information about logarithms. There's the quadratic formula. And in that same general area, you can look up that the surface area of a sphere is 4 pi r squared. Once you have an expression for the flux, stick that into Gauss's law. In other words, set the flux equal to Q over epsilon naught. Sometimes you have to come up with some clever substitutions to finish a problem off. This is not one of those times. We're supposed to solve for E. That's what the question asked for us, an expression for the electric field. So that's just dividing both sides by the 4 pi r squared. Divide both sides by 4 pi r squared, then rearrange things a little bit, and there it is. If you consider the special case where the charge is extremely small, if you imagine this spherical charge shrinking down to just a single point, it wouldn't change any of this. The answer would be the same. So what I've just done here is derive Coulomb's law from Gauss's law. One of the things I did the day before yesterday was basically derive Gauss's law from Coulomb's law. It's kind of arbitrary which way you want to look at it. You can think, if you want to think of Coulomb's law as being the most basic principle, you can derive Gauss's law from that, or other way around. Given Gauss's law, you can derive Coulomb's law from that. Well, this together with F equals Q times E. And the conventional way of looking at things is to think of Gauss's law as being the basic equation of electrostatics, and Coulomb's law as being sort of a special case that follows from that. But if you wanted to, you could look at the world the other way around, and that's an alternate viewpoint. But what we're going to do is move on to the next example. This time, instead of a spherical charge, you're going to have a charged sheet. Something like this piece of cardboard. Maybe I take the cardboard and I rub it all over my hair for a while. And through an amazing act of skill, manage to get the charge all uniformly distributed, so you don't have some places where there's a lot of charge and some other place where there's a little bit of charge. Actually, the math is, it's more convenient to think of it as an infinite sheet rather than one that's just 8.5 by 11 inches. Of course, what that means in practical terms is that the point where we're finding the field is very far from any of the edges, where very far means compared to the distance that point is from the sheet, the distance from that point to the edges is many times greater. So the edges are so far away, we might as well think of them as infinite. Step one, a sketch of the situation. We're seeing the situation here in cross section. In other words, the sheet is oriented like that, and somehow your head is in the middle of it, I guess. And anyhow, you got this positively charged sheet. It goes right, left, front, and back, all horizontal directions as far as the eye can see. What would the electric field around that look like? Electric fields point away from positive charges, okay? So above the sheet, the field would point up. Below the sheet, the field would point down. Furthermore, you would expect the charge to be, or you would expect the field to be uniform, because there's nothing any different about this point compared to this point over here. An infinite sheet, if you took the thing and you slid it over a few inches, there wouldn't be any difference. It would still look just the same. So any point that's a given distance from the sheet is in exactly the same situation as any other point, that same distance from the sheet. And so there shouldn't be any difference in the strength of the electric field. So I'm going to draw these field lines evenly spaced and straight up or straight down, because there isn't anything to make them point right or left. And again, if the plate is negative, that just reverses the direction. Step 2, let's pick a Gaussian surface. Well, over here, when we had a spherical charge distribution, a good choice for the surface was a sphere. Over here, when the charge is distributed across a flat surface, hopefully it comes as no surprise that the surface you want to pick, it has flat sides. You want to use a box oriented like this. Here's the sheet once again. Or at least the part of it's supposed to look like the part of the sheet that's behind the blackboard anyhow. Kind of a cross-sectional view again, as if you're looking down at it at a bit of an angle. Question says we want the field a distance L above the sheet. So the top of my box should be a distance L above the sheet. Symmetry is a good thing, so I'll make the bottom of the box the same distance L below the sheet. The point where you're finding the field should lie on the Gaussian surface. The top and bottom, hopefully you can figure out what's going on from my awesome artistic skills here, but the idea is that the top and bottom of the box are supposed to be parallel to the charged sheet, and the other 4 sides are supposed to be perpendicular to it. Maybe I'll label this point right here, point P. The idea being that's the point the question asks about. Okay, the question is asking me to get an expression for the electric field at point P. Worth writing that down. As I work through this, I'm going to need to refer to the area of the area of the top and the area of the bottom of the box are the same as each other. So I'm going to call them both A. Step 3, I need an expression for the total flux. I think if you look at the formula sheet, the way I wrote Gauss's law, it said the summation, I know I did this in Wednesday's notes anyhow. E dot A, the E vector dotted with the A vector, is E times A times the cosine of theta. The summation here would be to sum over the 6 sides of the box. There's no need to resort to infinitesimals and integrate, do an infinite sum, but we have to add up the flux through the top and the flux through the bottom and the flux through the right-hand side and so on until you've covered the whole 6 sides. So that's going to be the flux going out through the bottom. I might as well write this down as I'm going along. The field points outward through the bottom. The area vector also points directly downward from the bottom of the box. The area vector by convention always points outward. So E and A are parallel to each other on the bottom. Cosine of 0 degrees is 1. So the field through the bottom, which by symmetry would be the same as the field through the top. It's the same distance away from the sheet. Field through the bottom times the area of the bottom. And then there are the 4 vertical sides. These are, make a little model. The left-hand side of the box, for example. The area vector is perpendicular to the plane containing the area. The electric field lines are vertical. On the top half of it, they point up. On the bottom half of it, they point down. Well, either way, that's perpendicular to the area vector. Same thing on the front of the box. The area vector, again, perpendicular to the area. That's horizontal. The field lines are vertical. All 4 of the vertical sides have the cosine of 90 degrees, which is 0. So for those 4 terms, you've got a lot of nothing. And then finally, finish covering the entire surface, we also have to include the top. And just like the bottom, the flux through the top is E times A. So, put it all together, and the total flux through the entire box, all 6 sides, adds up to 2 times E times A, where E is the field on top of the box and A is the area of the top of the box. Step 4, plug that into Gauss's law for the flux. 2A equals Q over the permittivity. What the question asked for was the magnitude of the electric field, so just divide through by 2 and divide through by A. And I'm almost done. reason I'm not quite done though, is that when you're doing these types of problems, you need to give the answer in terms of the quantities that are mentioned in the question. A is something I made up as I was working along through the problem, okay? A is the area of this box I decided to picture in my mind when I got to step 2. It says the sheet has a charge per unit area of sigma. Well, Q over A, charge per unit area. The thing in parentheses is the sigma that's mentioned in the question. So I need to make that substitution. You see, because it's an infinite sheet, you can't talk about the amount of charge it carries because that's infinite. And you can't talk about its area because that's infinite also. So you talk about the charge density. In this case, the usual notation is if you've got a linear charge density, like, you know, if you had a charged piece of string or a wire or something like that, charge per unit length, they usually use the Greek letter lambda. For a two-dimensional charge density, charge per unit area, they usually use a lowercase sigma. For those of you who have a great desire to learn the Greek alphabet, capital sigma is the symbol we use for a summation. The Greek alphabet, like our own, has upper and lowercase letters. So I've often thought I should have, like when I was in first grade, there was this thing that went along across the top of the blackboard with, you know, A, B, C. I've often thought I should do that with the Greek alphabet in here. That might possibly be useful. And we could see, you know, alpha, beta, gamma, delta, zeta, eta. Anyhow. Linear charge density, lambda, two-dimensional, you know, an area charge density, sigma, three-dimensional, a volume charge density, rho, and that's the usual notation for that. So charge per unit area of this sheet over 2 times the proportionality constant from Gauss's law. Now, as a little sort of follow-up note, I said, what if you had 2 of these sheets with equal and opposite charges? Because that's a parallel plate capacitor, which is something that comes up fairly often in a course like this one. Like the chamber in the Millikan experiment. Some of you did it last week, some of you will do it in a few minutes, but that's what's in the chamber that you spray the oil drops between, is you've got 2 charged metal plates. What if one of them's positive and one of them's negative? Field lines run from plus to minus. If these are infinite sheets of charge, you'll have a perfectly uniform field in there. Realistically, as long as you're not too close to the edges, you'll have pretty much a uniform field. You get over near the edges, the field starts to get a little weaker. The field lines start to bow outward when you get near the edges. But as long as you're somewhere in the middle of the thing, so that you're far from any edge and our approximation of infinite sheets is valid, then it's a superposition problem using the formula that I just wrote over there. If you pick some point, maybe point P right there, the field, probably should have drawn this a little bigger so I had more room to write, but I'll do it bigger over here. If that's point P, somewhere between those plates, the field from the upper plate would equal the charge density over 2 epsilon naught. And U for upper, L for lower. Same formula. Because once again, it's the field of an infinite sheet. The only difference, if it's negatively charged, is that the field lines point toward it rather than away. But at any point in between them, those will be parallel. So when you apply the superposition principle and add them together, ½ sigma over epsilon naught plus ½ sigma over epsilon naught equals 1 times sigma over epsilon naught. If it's some practical situation, like the chamber in that Millikan device that's sitting over there, some practical situation where the plates are not in fact infinite, and you're just calculating the field somewhere in the middle between them, then you can make the substitution that sigma equals charge per unit area. Incidentally, the subtleties of the notation I was using is back over here where I was using a small q and a small a. That stood for a little bit of charge and a little bit of area. What was inside the box? Okay, a little bit of charge in the box, a little bit of area inside the box. Big Q and big A, that's the charge of one entire sheet and the area of one entire sheet. You stick that in there. The field between a set of oppositely charged, equal and oppositely charged parallel plates would be the charge on each individual plate, one of them positive, one of them negative. The charge divided by the area, also divided by the permittivity constant, except near the edges where the field would get weaker. Well, I started out with a problem where you had a spherical symmetry. Next one, I did a problem where you've got a rectangular symmetry. Guess what's left is a problem where you've got a cylindrical symmetry. So, number 5, you've got a long, hollow, uniformly charged. This time, instead of rubbing some sort of a sheet of something on my hair, maybe I've got a piece of PVC pipe and I rub it all over my hair. Okay, so I've got this uniformly charged tube, and I don't know where you would go to buy a pipe with a radius of 1 centimeter. In these parts, you usually get some sort of, ½ inch, 3/4 inch, 1 inch. But there's probably other parts of the world where you can do that. 2 centimeter diameter pipe. So how much charge per unit area is needed? 1 millimeter outside the surface, the field strength is going to be 1,000,000 volts per meter. There's a part B, but let's take care of part A first of all. Part A, step 1, is to get it clear in your mind, and a sketch on the paper probably helps you get it clear in your mind what the field looks like. For a piece of pipe, I think it's probably a good idea to draw a couple of different views. I have myself a side view and an end view. So from the side, so in this picture, I'm looking at it from the side, kind of like this. And that actually looks a lot like the charged sheet that I had in the earlier question. The field lines would point directly away from it, pointing upward above the pipe and downward below the pipe. For the end view, where you're looking at it like this, that's going to look kind of like the field of the charged ball that I had in the first problem. The field will point radially outward away from the piece of pipe. Step 2. Choose a Gaussian surface, which takes advantage of the symmetries in the problem. Well, we have a cylindrical charge distribution. For my Gaussian surface, I'm going to choose a cylinder, concentric with my piece of pipe. I'm going to call the length of the Gaussian surface. Well, L might seem like a logical letter to use for the length, but when you look up the formula in the formula sheet, the surface area, I used H for height, as if you had the thing, I guess I was thinking you got your cylinder standing up like this, and I called it H. So to go along with the notation that's in the formula sheet, we'll say that the length of this surface I'm imagining is H. I've got two different radii I'm going to want to talk about. I'm going to use a little r for the little radius and a big R for the big radius. Little r is the radius of the piece of pipe. Capital R is the radius of the surface that I'm imagining goes around the pipe. Little r would be 1 centimeter even. Capital R, like it says in the question, is 1.1 centimeters. The point where you're finding the field should be on the Gaussian surface. I'm going to label a couple of other things on here before I move the camera. The lateral surface area of a cylinder. Again, something you can look up in that mathematics section of your reference handout. Surface area of a cylinder, not counting the ends, is the circumference of the base. You know, think about it. If you had a tin can, like had a corn or green beans or something like that in it, you've cut both the ends off, okay? If you take a pair of tin snips and here's my can of corn. If you take a pair of tin snips and cut it so that you can unfold it like that, now you've got a rectangle, okay? The area of the rectangle would be its length times its height. Well, before you flattened it out, that length used to be the circumference of the base. So 2 pi r times the length, which, like I said, just look it up anyhow, so I guess I didn't really need to explain that. I'm also going to need the area of the part of the pipe that's within the Gaussian surface. That smaller area I'll represent with a little a. Two pi times little r times h. Okay, so that's all. I guess I can squeeze a little more on the bottom here before I move the camera. An expression for the flux. Well, we're not just talking about the, if it's a can of corn, we have to talk about the entire surface area of the thing, not just the curved part, but the area of the ends also. Gauss's law requires a closed surface. So you have to explain what happened to the flux through the ends. It's the same story as with the vertical sides of the box in the previous example. On the right and left sides, the area vector points out horizontally. The right-hand end, the area vector is to the right. The left-hand end, area vector is to the left. The field lines are vertical, so you've got the cosine of 90 degrees. The dot product makes the flux through the ends 0. In terms of pictures rather than formulas, the flux is telling you how many field lines pass through the area. And the only part of the cylinder that field lines actually puncture is the curved part here. On the ends, the field lines just skim along parallel to the surface. None of them actually pass through it. So the right and left ends, no flux. For the lateral area, the curved part, what's left after you cut the ends off the can, that would be E times A. The cosine factor equals 1 there. The area vector is parallel to the field lines at each point on the surface. And as I wrote a little further up, A is 2 pi RH, so there's my expression for the total flux passing through this closed surface. To be continued. Step 4. Gauss's law says that the flux through that surface is proportional to the charge within it. Step 5, I don't remember what step 5 was. Make any necessary substitutions and solve for what you need. This time, just for a little variety, I've done 2 in a row where it asked for E. Maybe it'd be nice to solve for something else. So, given the strength of the electric field, what's the charge per unit area on the surface of this pipe? This time it's sigma, the charge density. It's my thing I'm supposed to solve for. Well, that doesn't appear in the equation right now, so that would be the make any necessary substitutions part of it. Charge density, two-dimensional charge density. Sigma is the charge per unit area, which means, a corner on it there, I didn't mean to. Multiply both sides by A, and the enclosed charge equals the charge density times the enclosed area of the pipe. Now, back up in here. Well, actually, let's do it this way. As I wrote over there on the picture, the area of the pipe within the Gaussian surface is 2 pi times little r times h. So when I put it all together, a whole bunch of stuff is going to cancel out. The 2 cancels, the pi cancels, and the h cancels. Sigma is what I want to solve for. So that would be E times R times epsilon naught. I'll multiply both sides by epsilon naught. And to solve for sigma, I'll divide both sides by R. Just as a little footnote in passing, you might notice that the field of any sort of a line of charge, which is what this pipe looks like from the outside, it's 1 over r to the first power field. okay? With the charged sheet, I should have probably emphasized this back when I was doing that problem. It was r to the 0 power, as in where the field point was located was not part of the answer. I said that the point where I was finding the field was the distance L above the sheet, but there wasn't any L in the answer. The field is just the same everywhere, as long as you're not anywhere near the edges of the sheet. So for a sheet, effectively r to the 0 power, the field does not vary at all. For a one-dimensional charge distribution, like a piece of pipe or string or something, it's the field is a 1 over r to the 1st power thing. And yeah, because it's capital R. Capital R is the distance from the center of the pipe. So E is proportional to 1 over R. For a ball, like we did at the beginning of the period, it's 1 over R squared. For a dipole, like I did several classes back, it's 1 over R cubed. Not that you necessarily have to memorize all of that. I'm just pointing out that different charge distributions have different formulas. One way that people go wrong is you show them Coulomb's law and they just want to throw it at everything, whether it's appropriate or not. It's not always a field that obeys Coulomb's law. Anyhow, finish off part A. Part B is short. That'll only take a moment. I have to stick numbers in here. You look up the permittivity constant, and it's 8.85 times 10 to the negative 12 when measured in SI units. The strength of the electric field was given in the question, 3 times 10 to the 6 volts per meter. R is the distance from the center of the pipe to the point where we're finding the field. The question tells us that that's 1.1 centimeters, 0.011 of a meter. The radius of the pipe is an even 1 centimeter. So you get that number, and the units on it would be, after you get done, because there's a bunch of units on epsilon naught I didn't bother to write down. For that matter, volts per meter on this number here. And if you go through it and cancel out all the units and simplify it down, coulombs per square meter, units of charge per unit area. Or if you'd prefer to use one of the SI prefixes instead of scientific notation, sometimes it might be more convenient to call that 29.2 microcoulombs per cubic or per square meter. Part B. Part A was about the field that's a millimeter outside of the pipe. Part B asks about the field a millimeter from the pipe on the inside. What is E at that point? Well, so again, let's start with a picture. There's my piece of pipe, uniformly charged, a bunch of plus signs all over. For a Gaussian surface, this would be, looking into the end of the pipe. For a Gaussian surface, once again, choose a cylinder concentric with that pipe. This time, since the point where you're finding the field has to be on the Gaussian surface, this time it's on the inside Gauss's law says that the electric field on that surface is proportional to the charge within the surface. Somebody tell me, how much charge is inside of my little dashed cylinder here? Yep, none at all. All of the charge is out here on the pipe. And so Q equals 0 inside. So therefore, according to Gauss's law, what is the electric field on that, right? And that's going to be the case anytime you're inside of the charge distribution. In particular, a piece of metal under static conditions never has an electric field in it, because imagine you've got a conductor and you stick a couple of electrons in it, inside of it somewhere. Well, they repel each other. They want to get as far away from each other as they can. So as soon as you let go of them, they travel directly away from each other until they get to the surface. So any net charge on a conductor resides on its surface. And therefore, from this kind of thinking here, the electric field inside of a conductor is always 0. This is why they tell you that it's not such a bad idea to be inside of a car during a lightning storm, because of course, the fallacy with that is lightning can basically do anything it wants to. But there will be a tendency, at least, if there's a big shot of charge coming your way, for that charge to stay, assuming your car is made out of metal, which is not always a good assumption with some of the newer cars, but there'll be a tendency for the charge to stay on the surface. Now, the electric field is 0 inside of a conductor under static conditions. When there's a current flowing, that's a whole different story. But it's also a story for another day, because I'm 3 or 4 minutes over. So I will stop talking and get out the answer sheets for those of you doing lab number 2.